Next talk is by Haipeng Chen. He's from the Shenzhen Technology University. The title is the novel Assouad-type Dimension and Spectra, Theory and Recent Progress. Haipeng, please.
Thanks, Zhiqiang. Thanks the invitation organization and Zhiqiang and the ISQGD research group. And it's my great pleasure to give a talk in the workshop on fractal geometry. Also, is a workshop of the first workshop in the ISQGD session. Um, my topic today sorry, is the lower Assouad-type dimensions and spectra theory and recent progress. And this is a joint work with so many peoples, but I will mention them just in cases. And so we first go to the introduction about fractals. Fractal is the is widely happens in national worlds and just natural worlds and the just the mathematical objects. For example, we can see the Bocoris, and this is one of the famous example in fractals. And the next one is the Barnsley firm, just a natural approximation of the Barnsley firm. For the third one and fourth one, the third one is a tiling of this one called snowflake, and the fourth one is the graph of domain function, which also known as the popcorn graph, which will be used on this talk later. As we can see, just the fractal is a natural object happening in natural worlds and the math societies. A way to describe or to quantify or qualify the dimension, the fractals is the dimension. Dimension theory is one of the one of the important and natural topic for the fractals. There are many different ways to define the dimension of a fractal, and each capturing a different aspect of its geometry. For common definitions of dimensions, we will talk about the class. As for the classical stuff, we will discuss the house of dimension, packing dimension, upper lower box dimension, which is known as the dim B or dim M. And in this talk, we will talk about something like this. And for the next one of the just recent popular dimensions are Assouad-type dimensions. They include Assouad dimension, lower dimension, quasi-Assouad dimension, quasi-lower dimension, etc. And for the third stuff, just for the other dimensions, including modified box dimension, topological dimension, and Fourier dimension, etc. The core intuition on the dimensions are for involving quantifying how a fractal fills up space on small scales. But there are many ways to do this, and we will talk a bit later. And focus on the talk today. For simplicity, I will focus on the interplay between the lower dimension, house of dimension, box dimension, or Minkowski dimension, and Assouad dimension. A central theme in dimension theory is that is to understand how distinct notions relate to each other. Just to say, when these dimensions coincide with each other or when they will differ from each other. Um, let's have a quick review about the dimensions. One of the classical and well-known dimension is the house of dimension. That XD be a metric space and E is a subset of X. And for any S and for any delta, we define the S-dimensional delta measure like follows. And we have to be clear of something that for the diameters of the UI, it's just no more than delta, but it can be choose arbitrarily small, or sometimes close to zero. That's okay. And by the S-dimensional delta measure, since it is monotonic with respect to delta. So we can also define the S-dimensional Hausdorff measure like this, since the S-dimensional delta measure is monotonic. And as for the Hausdorff measure, since it has just the critical themes, so there exists a value, a critical value S, such that for the Hausdorff measure, if t is strictly smaller than S, it is infinite. But when t is larger than S, it will be zero. And we say the critical value S is the Hausdorff dimension of E and denoted by dim HE. Compared to the Hausdorff dimension, another dimension is called Minkowski dimension or called box-cunning dimension. And in this talk, I'm sorry at first, perhaps I would abuse using the box dimension or in Minkowski dimension throughout this talk. And let's have a quick review about the Minkowski dimension. Let E be a non-empty bounded subset of Rn, and for any epsilon, positive epsilon, let n epsilon e be the smallest number of balls of radius epsilon such that it covers E. And we just take the log and we take the log law and taking infimum of this log surf, we call it the lower box dimension or lower Minkowski dimension. And as for the log law, if we take the supremum and limit supremum, and we call this a value is the upper Minkowski dimension. If these two values coincide, we call the common value the Minkowski dimension. Just say if the limit of log exists, and we call this value the Minkowski dimension. One thing we should be clear is that as for Hausdorff dimension, we do not have strong restrictions of the diameter. It just say as for the Hausdorff measure, a Hausdorff dimension, just the diameter is no more than delta, that's fine. But as for the Minkowski dimension or box dimension, the just the choices of the diameter is strongly restricted to the value of epsilon. So this could be the main difference of this. Um, and as we can see, both Hausdorff dimension and box dimension or Minkowski dimension focus on the global settings of the set. And compared to the Hausdorff dimension and Minkowski dimension, the Assouad-type dimension focus more on the local settings of the set instead of the global settings. Um, let's have a look about the definition of Assouad dimension and the lower dimension. Let E be a non-empty subset of the metric space X, and for any small r smaller than capital R, let n smaller r E intersects B XR be the smallest number of balls of radius R needed to cover the region E intersects the ball. And also dimension is the infimum of all S such that there exists a constant C such that for any small R cover of the capital R ball, it can be controlled by the capital R of small r with the exponent of S. And for the lower Assouad dimension, it's a supremum of all S such that the small r cover of the capital R ball can be controlled by the as for the lower bounds for the control can be controlled by the capital R divided smaller r to the exponent of S. Um, these two the Assouad-type dimensions. These two Assouad-type dimensions says it focus more on the local settings or just focus on the certain local theme of the set instead of the global things. So, roughly speaking, you can treat it as the local Minkowski dimension of the local settings. Well, after these definitions, we have a quick review of the example, just the countable set with distinct dimensions. And for the example, I would like to introduce one of the famous and the well-studied example, just the polynomial decaying sequence. also known as the decreasing sequence with decreasing gaps. Fix a parameter p and consider the set like this. And this set is known that it will be 1 to 2 of p and 1 to 3 of p, etc. And as for the settings, if you if you would like to try as an exercise, you can check it for details. But if you are not interested in the details, you can trust me. Based on the simple calculation, you can see that the household dimension is zero, since by you can also say by the countable stability of the set, and you can also construct the measure like this. And as for the Minkowski dimension or box dimension, it will be a 1 to 1 plus p. And compared to the house of dimension and Minkowski dimension or box dimension, the Oswald dimension is 1, since the set we see it focuses more on 0, and the lower dimension is 0, since every point here is the isolated point. And the key point for the calculation is that for any p, these dimension notions provide three distinct values, like house of dimension, box dimension, or Oswald dimension, or lower dimension, box dimension, and Oswald dimension. This illustrates that countable forces a house of dimension equals 0, isolated points forces lower dimension to be 0, and the local structure keeps Oswald dimension at 1. Well, um, another topic for the fractal dimension is the general properties. And a reasonable definition of the dimension of the set typically satisfying the following settings, like monotonicity, finite stability, countable stability, Lifshitz property, held property, closure invariance, and open set condition. However, I would like to say that not all dimension notions satisfy all properties. Um, let's have a look about the chart for properties of dimensions. For house of dimension, it satisfies monotonic, finite stability, composite stability, Lipschitz, Helder, and open set, except the closure. However, compared to the house of dimension, the Minkowski dimension fails in countable stability but fits in the closure property. As for Oswald dimension, it says it satisfies monotonic, finite stability, closure, and open set. However, compared to the older dimension above, the lower dimension only satisfies the closure properties. Even it also says lowest dimension fails for monotonicity. Um, Here I would like to say some remarks. For the stability, notice that the lower dimension is a rare example of a dimension such that fails on the monotonics. For example, if E is an interval and X is an isolated point, and the lower dimension will be 0. As for the countable stability, only half of dimension satisfy this, and making it the most suitable for measure theoretic analysis. For the open set property, um, this could be shown for the lower dimension since there exists an open set such that the lower dimension is 0. This will be quite strange and different from other dimensions. Okay, so why we say something more about the Oswald dimension or Oswald type dimensions, since the Oswald type dimensions will it describe something on geometric properties of metric spaces. For example, we have a look about Oswald dimension first. One of the geometric property in in metric space is the doubling property. A metric space is a doubling metric space if there exists a constant, a uniform constant n, such that for any ball, for any just center x, and for any ball with a radius r, can be covered by at most n balls of radius a half. Just say, um, the for any ball with the a half r covers is bounded, and as for alpha dimension is a way to describe whether the set or a metric space is doubling. It says a metric space have finite alpha dimension if and only if it is a doubling metric space. Well, it means that if X is a doubling metric space, it can be checked by its Oslo dimension. Also, if the Oslo dimension of the space is finite, we can also say it is a doubling metric space. And to some extent, doubling metric space can be approximately similar to the Euclidean space for geometric properties. Compared to the Oslo dimension, the lower Oslo dimension also available to describe the geometric properties of metric space, but not for doubling for another property called uniformly perfect. Um, let's have a quick review of the uniformly perfectness. A metric space is uniformly perfect, except it says if there exists a constant C such that for every x and every smaller r, the set BXR and divides BXR to the C is not empty whenever just X to the BXR is not empty set. So it means that if a set is uniform perfect, so it says if for any ball and we cut out just a smaller region of the ball and it still have some points on the just a ring section instead of the empty ones. Well, a famous theorem for uniform perfectness is that the from anti-Kamak et al. And it says a complete metric space have a strictly positive or Oswald dimension if only if it is uniformly perfect. So it says if the set is uniformly perfect set and its low Oswald dimension will be strictly positive. Also, if you see some sets has the strictly positive lower ortho dimension, it is a uniform perfectness. And one of the example for the lower for the uniform perfectness is the ternary contour set. Since you erase any if you have any ball and erase a smaller ball, for example, like a third or one of nine, and you can see the regions still have some points of the ternary contour set instead of the empty ones. Also, as for the notions of low ortho dimension, it is based on these properties. It is also known as uniformity dimension. Well, as for the application of Assouad-type dimensions, it can be applied to some geometric properties and the other branches of mathematics. The Assouad and the lower Assouad dimension play critical roles in geometric method theory, conformal geometry, and other branches of mathematics, like embedding theory. One of the famous results in embedding theory is the Assouad's embedding theorem, but I will not go deep inside into this result today. And the Oswald type dimension also available for describing the dimension of the set from Diophantine approximation. One of the results can be found from Daza and his collaborators. Also, the Oswald type dimension can be applied into the harmonic analysis, like maximal operators and Hardy inequalities, like Andy Kamak and Rohrbach, Beltran, etc. So this could be just a quick and general result of the dimensions. And as for the fractal dimensions, a natural question is to describe the relationship between these dimensions. One of the topics, the fundamental inequalities of non-dimensions. We see that for any abounded set, following inequalities holds. Just says if we consider the house of dimension, Minkowski dimension or box dimension are also dimension. House of dimension is the smallest one, and the lower box dimension, then the upper box dimension are also dimension. If we consider only the covering settings, just say if we just consider the lower dimension, box dimensions are also dimensions. Lower dimension is the smallest one, then the lower box dimension, upper box dimension are also dimension. However, here I would like to mention that in general, lower dimension and Assouad dimension are not comparable. For example, just say a famous result from a Lamar set. For complex sets, the lower dimension would be strictly smaller than the Hausdorff dimension. There's also an important aspect in the Diophant approximation, but but here I would like to emphasize that the result does not hold for non-empty set, not for non-compact sets. For example, if we consider the rational points in 0, 1 interval, the Hausdorff dimension is 0, but based on the closure properties, the lower dimension will be strictly 1. So here, just like to say, if a set is compact, you can use the lower dimension for the lower bound of house of dimension. However, they are not comparable in general. Um, Another question is that is there a set such that all the dimensions coincide? So here's a good thing that if E is an alpha regular set, which Shah introduced just now, and then says if the set is alpha regular, the all dimensions coincide. Another thing is that there also exist examples such that all the dimensions differ from each other. For example, like the homogeneous Moran sets or homogeneous counter set, etc. So the dimensions are not always coincide, and sometimes they will. If the set is alpha regular, just good enough, you can see it. They are coincide, but if the set is not so homogeneous like the alpha set, and the dimensions will all differ from each other. So this involves this also involves the topic about the dimension interpolation. The dimension interplay general framework on the dimension interpolation is to say, given two-dimensional notion, smaller dim and capital dim, satisfying that the smaller dim smaller than the capital dim, we define a interpolation dimension, the theta. The theta range from the 1 unto the real numbers, which satisfies the things like boundary values. Just say um, the D0 is the small one, and D1 will be the capital ones. And boundedness, just to say the interpolation function ranges between the smaller dim to capital dim. Also, and the function is continuous, and the function D is natural and give rise to a rich theory. So why we consider the dimension interpolation? The first thing is that for the deeper insight of geometric properties or analytical properties of sets, just say it use better understanding of the endpoints and smaller dim and capital dim. Also, for this, the interpolation also gives some information about the phase transitions of dimensions. Just say we witness one type of geometric behavior changing into another one. The third thing is that it provides more structural information and enables better applications. Also, give us a new set of open questions. Um, in this years, just here are some several good examples and successful examples on the dimension interpolation. Um, the dimension, since we see the dimension often captures only extreme scaling behavior. For example, like the local settings, the alpha one gets the thickest part, and the lower one gets the thinnest part. And for global averages, the house of dimension is dedicated for the measuring properties, and the Minkowski dimension or box dimension just gives the covering properties. So the rule of spectra is to observe the structural transitions on multi-scale geometry, and then we study dimensional spectra, which interplays between these classical dimensions. The mainstream or just the popular dimensional spectra include these followings. One is the upper spectrum and the lower spectrum. This bridges the gap between the box dimension and the upper dimension or lower dimension. The next one is the intermediate dimensions. The intermediate dimension is a continuum of dimensions between house of dimension and box dimension. Another thing is the Fourier spectrum. The Fourier spectrum relates to the decay of Fourier transform of meshes. and it ranges from the Fourier dimension to the Hausdorff dimension. However, we do not mention more about the Fourier spectrum today, since it beyond the scope of this talk. Well, let's go to the definition of the Assouad spectrum and the lower spectrum. For any theta, the Assouad spectrum, the lower spectrum is introduced by Fraser and Yu, Zhang and Han in 2018, evaluate the scaling of E by fixing the relationship between the two scales small r and capital R. Um, let's have a quick review back to the Assouad dimension and the lower dimension. As for the Assouad dimension and lower dimension, there are no restrictions of the capital R and smaller r. Just to say, if we just have the smaller r smaller than capital R, and just to consider the ball covering values. However, as for the Assouad spectrum and the lower spectrum, it gives a strong relationship of the smaller r and capital R by giving smaller r be the r to the power of 1 to the theta. Just say if the Assouad spectrum is the inform of S such that there exists constant C such that the smaller r is restricted by the capital R to the power of 1 to the theta, and the S may also change it into the capital R to the S times 1 minus 1 to the theta. Also, the lower spectrum is the supremum of all S, such that there exists constant C. And then for the ball covering here, just have the lower bound controlled by the capital R with the exponent S times 1 minus 1 to the theta for all R ranging from 0, 1. So as for the Assouad spectrum and the lower spectrum, it also focuses on the local properties of the set, but it differs from the Assouad dimension, the lower dimension, since it gives a strong restrictions between the small r and capital R by a relationship that the smaller r equals to the r to the exponent of 1 to the theta. Um, let's have another example. Let's have a back to the polynomial decaying sequences for the just the dimension spectra. We still have we still discuss the decreasing sequence with decreasing gaps, and then we still describe the F here. Um, for fixed NP, and we consider the decreasing sequence with decreasing gap here. We know that the Hausdorff dimension is 0. A box dimension, a Minkowski dimension could be this value, and also dimension equals 1. Also, we see the lower dimension is 0. But as for the dimension spectra, the lower spectrum also be 0, since isolated points everywhere, so it gives the lower spectrum equals 0. As for the Assouad spectrum, there is a formula, exact formula like this. And this formula means if the theta is smaller enough, it looks a bit more to the box dimension than the Assouad dimension. However, when the theta ranges from some larger ones, it gives the information more on Assouad dimension than the box dimension. So this use a phase transition of the Assouad spectrum. So the dimensional spectra here just say the Assouad spectrum will give some phase transitions from upper box dimension to the Assouad dimension, and the lower spectrum looks a bit just the lower dimension. So as it always holds for like this, and this used to discuss the basic analytical properties of the Assouad-type spectrums. We first go to the information about the Assouad spectrum. The Assouad spectrum provides a continuous transition between global and local settings. Just to say, it ranges from the upper box dimension to the Assouad dimension, and you also use a phase transition like this. And its ability is characterized by the following properties. Just say, um, for any bounded set E, and the mapping just the Assouad spectrum is continuous on 0, 1 open interval. Furthermore, um, the limit behaviors of the Assouad spectrum also holds. Just to say, if theta tends to 0, the Assouad spectrum will approach to the upper box dimension or the upper Minkowski dimension. However, when theta tends to 1, the Assouad spectrum will approach to another notion called the quasi-Assouad dimension. The quasi-Assouad dimension is a value could be strictly smaller than the Assouad dimension for some sets, but we will not say something more about that since it's a bit beyond our topic today. Moreover, we have the general dimension chain like this. Just see upper box dimension is a smaller one, and the Assouad spectrum, quasi-Assouad dimension, and the Assouad dimension. Also, it is possible to say that these inequalities will be strictly different from each other. Just to say, as for the Assouad spectrum, although it can approach to the upper box dimension, but it sometimes fails to reach the Assouad dimension. Another thing is the final continuity estimates of the Assouad spectrum. So let E be the boundary set, and then for any theta 1 more than theta 2, the Assouad spectrum satisfy this continuity estimates. These estimates use that just to say if we just erase the one to minus theta 1 to put them into this region, it just say for the for the shape of the 1 minus theta times also spectrum with respect to theta, it's a continuous monotonic and the Lipschitz function. And this it estimates reflects that the continuity also spectrum and gives something more than the also spectrum itself. Um, Based on the continuity estimates, we can interpret it like this. So here just say for any set, the also spectrum satisfy this. And the natural question is to ask, is it possible for all dimension for all functions satisfying these properties? And is it possible to have a set such that the also spectrum of the set is a function? This also known as the attainable forms of the classification of Assouad spectrum. Um, in 2024, Alex Ritter gave a complete give a complete characterization of the Assouad spectrum, just like the following. Let ED be just be the natural number, and phi be a function. Satisfy that one for any lambda more than theta, and the function phi satisfying this inequality, and he proved that for any phi satisfying this, if and only if there is a set F such that the Assouad spectrum of F is defined theta. So this is a significant, an important result for the characterization of Assouad spectrum, since this result fully characterizes which functions can appear as the Assouad spectrum of a subset of Rd. And it just gives us, it's just, the result says that if the function satisfying this property, and this can be available to find a set such that the Assouad spectrum will be this and phi. Moreover, if the Assouad spectrum, if a set, if given a set, and when we consider its Assouad spectrum, it naturally satisfying these inequalities. Moreover, um, we just say the Assouad spectrum just ranges from the upper box dimension to the quasi-Assouad dimension, and we say the quasi-Assouad dimension will be strictly smaller than the Assouad dimension. Another topic is to say, is there any other dimension spectra can recover the interpolation between the quasi-Assouad dimension to the Assouad dimension, or just to give the complete interpolation between the box dimension, upper box dimension to the Assouad dimension. Um, First, we introduce the definition of the dimension function. We say that the dimension function is a dimension function if the following two conditions holds. The first one is that the capital R to the phi R log 1 of R increases to infinity as R decreases to zero. And the next thing is that phi R decreases as R decreases to zero. And the dimension function can be treated as a generalization of the exponent of the capital R divided small r stuff. And then based on the dimension function, we have the definition of the phi Assouad type dimensions. The phi Assouad dimension and the upper phi Assouad dimension of the set, denoted by the Assouad phi and dim A phi and overline F, respectively, are defined as follows. Now we have a look about the general Assouad dimensions. We first have a look about the the phi Assouad dimension. The phi Assouad dimension is the infinite of the exponent s, such that there is a constant c, such that for any capital R and for any small r, which is strictly chosen as the r to the 1 plus phi r, and the ball covers of small r of the region F intersects B capital R. It can be controlled by the R. Um, it can be controlled by the R to the phi rs here. And as for the upper Assouad dimension, it also gives the infinite of S such that the things holds. However, here sorry for the typo, since here should be capital R divided smaller r to S. And the interpolation, um, why we consider the interpolation of the Assouad-type dimension, as the study of generalized Assouad dimension was inspired by John and Han in 2018. Also, Ignacio Garcia et al. Extended this framework to some general dimension functions to capture the finite geometric structures. And when we're considering about the general chain like this, just the upper box dimension will be smaller than the phi Assouad dimension, and will be smaller than the upper phi Assouad dimension, and smaller than Assouad dimension. And recently, Arman Banerjee, Alex Ritter, and Sasha Chowdhury in 2025, they proved that the phi Assouad dimension can fully interpolate from the upper box dimension to the Assouad dimension. The result says for any unbounded doubling space F and for any value alpha here, satisfying the upper box dimension to the Assouad dimension, there exists a dimension function phi such that the upper phi Assouad dimension equals to the phi Assouad dimension and equals to the alpha. Just to say, the generalized Assouad dimension can fully interpolate from the upper box dimension to the Assouad dimension by the function phi instead of some parameter s here. This implies that the generalized Assouad dimension fully interpolates between the upper Minkowski dimension and Assouad dimension. Well, compared to the well-studied Assouad dimension, the natural question, or just similar question, will say, how about the lower Assouad dimensions? Since we see the lower Assouad dimension is a natural dual to the Assouad dimension, so based on the Assouad dimension settings, we have the continuity estimates, limit behaviors, and interpolation theory and classification. So how about the lower dimensions? As for the theory of lower dimensions, we will separate into three parts. The first one is the general theory. Just can we say something on the thinnest part of the set by lower spectrum or lower dimension? Another thing is that is it possible to say something about interpolation on lower type dimensions? Just to say it, can we say something for the interpolation between the lower dimension to the lower box dimension? Another thing, the third one is can we say something on the classification or attainable forms of the lower Assouad spectrum? Just to say what types of a function guarantees that the existence of a set such that the lower spectrum will be phi theta for all thetas ranging from 0 to 1. Let's go to the basic properties of lower spectrum at first. So For the lower spectrum, the general properties of lower spectrum, the lower dimension is the smallest one, and a value called a quasi-lower dimension, and we just you just treat it as a value here, but do not focus too much on the definition here. And the quasi-lower dimension will be the second one, and smaller than the quasi-lower spectrum, and smaller than the lower spectrum, and smaller than the lower box dimension. Also, there is a set such that the lower dimension will strictly smaller than the lower spectrum and strictly smaller than the lower box dimension. Um, Another thing is the continuity estimates of the lower spectrum. So the map of the lower spectrum is continuous until one. Its special setting is to say if you are interested in the detailed computation, you can find that the lower spectrum satisfy the lower bound estimate like this, and also it's also satisfy a final lower bound estimate like this, and the upper bound estimate like this. Also, the use of the lower spectrum is continuous on zero open intervals, and the Lipschitz continues on the any closed intervals, subintervals in zero one interval. Unlike the Oswald spectrum, the lower spectrum behave differently near the endpoints. First, we have the result of the existence of limits. Just to say, for any empty bounded set F, the limits of the lower spectrum as theta to 0 and theta to 1 always exists. Also, the limit to the lower spectrum. Sorry, here should be here's a typo. Here should be the lower spectrum as theta tends to 1 is the quasi-lower dimension, where the quasi-lower dimension would be strictly larger than the lower dimension. While for some sets, the lower spectrum approach to the low box dimension as theta tends to 0, but this is not true in general. Here, just to say, there exist examples such that the quasi-lower dimension will be strictly larger than the lower spectrum at first. Moreover, there exists a compact uniform perfect set such that the lower spectrum will be strictly smaller than the lower box dimension, and this also use that the lower spectrum when theta tends to 0, it could not interplace the lower box dimension. So, as for the lower spectrum, although it is good enough to recover some part of the interpolation, but it fails for some if it fails for two parts of like the lower dimension stuff and the lower box dimension stuff. And just a natural question is to say, since we see the phi alpha dimension can successfully interplace from the upper box dimension to the alpha dimension, so some will ask, is it possible to see the phi lower dimension also interplay from the lower dimension to the lower box dimension? We have to record the dimension functions again, and it just should say the dimension function is says a recovery about the capital R divided by small r by the function phi instead of the exponent s, and the lower phi lower dimension of the set are defined as follows. Sorry for the typo here inside. Here should be a supremum. And as for the phi lower dimension, it means the supremum of S such that there is a constant C such that for any smaller r, which strictly equals to the capital R to the 1 plus phi r and smaller than the small capital R, and the lower bound of the ball covers can be controlled by the R to the phi r here. Also, the lower phi lower dimensions is just to the difference is that for the lower phi lower dimension, the smaller r can be chosen arbitrarily smaller than r to the power of 1 plus phi r. And the main thing is to also consider the lower bounds too. And as for the interpolation of generalized lower dimensions or lower phi dimensions, the positive things are um, for the quasi-lower gap, it successfully it fills the gap. Just to say, we analyze interpolation of low type dimensions by divide into the range into three regions. For the first regions from lower dimension to the quasi-lower dimension, um, the the standard just the lower spectrum cannot reach this value, but generalized lower dimension can fill the gap. Just to say, for the generalized phi lower dimension, it can interpolate from the lower dimension to the quasi-lower dimension, as the theorem shows. For the region 2, for the S of the limit to 1, just the low spectrum as limit to 1 and limit to 0, for these regions, the interpolation naturally holds from the continuity of the low spectrum. So here, and this on this slide, it says the generalized and lower spectrum and the lower spectrum combined together can fully interpolate from the lower dimension to the values of limit to 0. However, the generalized lower spectrum fails for the limit 0 to the lower box dimension. So the following result says there exists a set such that for any dimension function phi, the lower spectrum, the generalized lower spectrum, and the lower spectrum itself will be strictly smaller than the modified lower spectrum or the phi low modified lower spectrum, and it will strictly smaller than the lower box dimension. Where I would like to say what is the phi modified lower spectrum is the lower spectrum, phi lower spectrum of the subset E of F, with the supremum of the all the lower with all the phi lower dimensions. What is the counterexamples? The counterexample is illustrated by the popcorn-like pyramid sets, also you can treat as the most original one, the popcorn function. Um, let's have a look about the first figure, the first slide of the figure. This one is the popcorn graph, also just a very origin of the popcorn-like pyramid sets. Since we see they're isolated everywhere, so if we consider the lower type dimensions, including the lower dimension lower spectrum or the generalized lower spectrum, they all coincide to 0. If we consider the modified lower ones, since we see um, the line here, the line segment here is all the irrational numbers. So the lower spectrum is the modified lower dimension is 1. However, for my recent result shows that the popcorn graph, the box dimension of popcorn graph is for the 3, so which is strictly larger than 1. So this use that. So these all use that just the as for popcorn graph, so they exhibit a strict gap that no dimension functions can bridge from the limit 0 to the low box dimension. Furthermore, they indicate that the modified lower dimension and modified the lower spectrum also fails for the interpolation of this region. So to sum up here, just say for the lower spectrum, it is in place for a part of the lower dimension to the lower box dimension. And as for the generalized lower dimension, it interplays fully from lower dimension to the quasi-lower dimension. But both lower spectrum and the generalized lower spectrum fails for the limit 0 to the lower box dimension. Just to say the generalized low spectrum fails for the recovery of low box dimension. So this is the interpolation stuff. Another thing is the attainable forms, or just to say the classification of lower spectrum or lower dimension. Um, Recalling that for any F, just for any theta 1 smaller and theta 2, the lower spectrum satisfies these two inequalities. And motivated from the continuity estimates of the lower spectrum, one may ask the following question. So given lambda smaller than alpha smaller than d, and if dimension for any function phi satisfying these two inequalities, and these two inequalities just the interpretation of this the properties of low spectrum. So if the phi satisfying these two inequalities is there a set F such that the lower spectrum will be strictly equal to the phi here? So one of them, some will ask this question like this. However, for the general settings, it's quite hard to directly use this for the classification of low spectrum. Here I would like to say special cases which will be positive, but in general cases it will remain much harder questions inside. So we say something about for general theory of homogeneous sets. So what is homogeneous set? So we say the set F is called homogeneous if the local geometry is uniform anywhere. Just to say, for any 2 points x, y in F and given two scales, smaller r and smaller than capital R, and the ball covering numbers will approximately the same number, just up to a constant of c. Here, just to say, mm, as for the homogeneous set, it says if we have the ball of capital R, no matter where it is, and as for the smaller r of the capital R cover, um, it approximately same up to a loss of the constants. So, what can we achieve from the homogeneous set settings? So we say if for homogeneous set, we have the following inequalities, and this is a great upgrade from the general cases. Since for general cases, it will be just theta 2 times something minus theta 1 times something. But for the homogeneous set, we can erase the theta 1 and theta 2 in this region, but just actually use it. Um, also, what can we say something or more about the homogeneous sets? Here, just to say, can we say if we can replace the next inequality by the homogeneous sets, can we say something about for the attainable forms of the classification of low spectrum? Um, the answer for the homogeneous set is yes. So here, just to say just to simplify the construction of the function. So here, just from 0, 1 by the exponential function, just just take it from the 0 to infinity, and then we construct this function like this, and by um by the results of AMLA and Alex, we also say for homogeneous settings and for the G like this, and we can say there exists the homogeneous Moore set such that for any theta, the lower spectrum will be defined as the homogeneous sets above. Um, just here is the just the recent progress on the low spectrum. Finally, I would like to say something about the further questions on the low spectrum. The first question is that can we say something more about the low spectrum as theta tends to 0? So, is it possible to say something more about the general geometrical settings between of the limit zero stuff, or can we say some more connections between the lower spectrum, which with theta tends to 0 and the low box dimension? Another question is that is any other possible dimension spectra interplays between the lower spectrum to the low box dimension? And the third question is that can we say something for the general classification of the lower spectra? Well, that's all of my talk again, and thanks again for the ISQGD committee, and thanks for the organization from Zhiqiang and invitation again. So that's all for what we speak today, and thanks all the attention here. Thank you all of you. Yeah,
Okay, thanks for Haipeng's talk.
thanks, Zhiqiang. Yeah.